Okay, let's continue. So last time we start with some property of the web graph, right? Like the connectivity we show here. Okay, so basically we said that given any graph, right, you can partition the graph into a set of strongly connected components. And then the remaining graph connecting the ICCs is a DAG. So, right, so for the next quiz, all those kind of properties may be asked. Okay. What is the real internet, the web graph, right? So first, the web structure is not static, right? And it's growing much larger over time. Right? So what we have is the data back to 2000, right? At that time, it's already fairly large. So it has 203 million web pages, and there are over 14 million links, right? Connect them. Right? On average, each web page contains like 7 links. Even this one, it's already raised a computational challenge for computer at that time, right? Nowadays, of course, we have much more powerful computers, right? But the web graph is probably even larger. So it's still a computational challenge to get the web structure and do the computation. Right? I think even Google is hard to know the real kind of a complete web structure. Right? So I think this data set is already represented enough for this one. Right? So basically, here we have the ICC, the largest strongly connected component, is roughly 30% of the nodes. Right? So this is a fairly large, 56 million nodes. While the second largest ICC is only 150,000 nodes, which is way more smaller than the first one. Right? You can compare, right? It's less than 1% of the largest SEC. Right? So question here, anyone can explain why the second largest SEC is so much smaller than the largest one? You can just unmute yourself or put in the chat.
Well, if it were much larger, then there's a higher probability it would just be grouped into the largest one.
Yeah, great, perfect. Right, that is a reason. So we shouldn't expect to say, right, the second largest one that is also fairly large, right? Otherwise, these two may merge into one large SSD. Okay. The second is that the largest weakly connected component means that, right, if you take the link from directional to unidirectional, right, and then you consider whether it's connected or not, then this one contains 90% of the nodes, right? So this is very high. Question here, right? Why the WCC is so large, right? It's 90% of node. Okay, right, you can unmute yourself or put in the chat. Why this weakly connected component is so large? Okay, so basically there are, I think, at least two reasons, right? The first one is that uh, the weakly connected component is easier to merge, right? So like the first one SAC, right? The second SAC, right, cannot be merged because you need the two directional circle, right? There. But for weakly connected component, because the edge have no direction, right? So you are more likely to merge those two smaller SAC into one. Right? So the basically consider from other, in other words, right? The largest SAC can swallow more smaller SAC to become a larger one. Another reason that is if it's not connected, if consider the nodes that are not part of the largest WCC, right? What does that mean? Right. So that means those nodes kind of they are basically separated, right? And when they are separated, it's very hard for the crawler, right, to find them. Right? Right. So theoretically, it is possible that there may be a large number of nodes, right? Actually, they exist, but the crawler just cannot find them, right? So the crawler basically, you are giving some starting point. Just try to go from the web page, right? Follow the link to find those pages. So if you are not part of the SACs, the large SAC, then it's hard to be found by the crawler, right? So from those reasons, you can see the WCC is very large. Okay, this is the bow tie graph, right, of the web page. So in the middle, this is the core of the network, right? So those are strongly connected, and they are part of the yin, right? So meaning that they point to the core web pages, but the web pages does not point to them, right? So those are normally just the new pages, right? Or there are some out part, this part is basically the core pages point to them, but they don't point back, right? Those are example like corporate pages, right? They just, or some information pages, they contain information there, right? But they don't point to others, right? Other than that, there are some tendrils and tubes, right? And there are some disconnected small components, right? So that is roughly 10%, right? Because all the remaining part is WCC, right? But those ones are disconnected component, right? Theoretically, it's possible that we may have some web pages there, here, right? We cannot find them, right? So in order for the crawler to get it, you need to find some web pages inside it, right? But if you don't have those, you can consider that a seed, you just cannot find them. Right? So basically, for the web pages, we can see, right, it looks like this. Right. Okay, now let's come to the diameter. Right? How long are the paths there? This matters because to find the information on the web pages, right? Sometimes you need to go through multiple steps. Or in a social network, right? To connect to someone, right? You also need to go through some steps. Right? So clearly, the the larger the diameter is, the more challenging for you to find someone or find some information. So there are two common notions for the diameter. One is the maximum distance between any two nodes. The other one just the average distance between any two connected nodes, right? Because if they are not connected, the distance is infinity, right? It's not relevant. Okay, so the numbers from the figure in 2000, right? The maximum diameter of the ICC, right? So we don't know exactly the number because computational is also hard. So we know that it's at least 28, right? Or for the whole graph, if we consider the WCC or other component, right, it is even larger, more than 500. So which means if you really want to say the worst case, right, it takes a lot of steps. So the average one, if we take the average distance, right? So this one is much better. It's only 16.2, right? And if you treat the edges as unidirectional, means that like a friendship, right? On the social network is bidirectional. Right? In that case, the average diameter is only 6.8. Right? This is like the sixth degree of separation. Right? So well known, right? So surprisingly, on the social network, right, you can reach an average, right? Reach anyone in the world, right? Also, of course, on the social network connected, right? In just 6 or 7 steps, right? So this one uh, seems very small, right? But if you think about, right, even if you want to connect to someone in Africa, right? So here in the US, within several steps, right, you probably can connect to, for example, within 2 steps, you probably can connect to the president of the university. And even from there, you can connect to the governor or the president, right? And from there, you can connect to the president in the other country and follow this way, right? So if you think that way, that is actually not that uh, unbelievable, right? For this such a short path to exist, right? But of course, engineering, how to find this path, it's not that easy, right? The other question is that how has the diameter changed over time? Because when the network is small, right, it's very easy for people to know each other, right? Or even in several steps, right? In your in your class, right? You probably know each other, or you even within 1 or 2 steps, you get to know everyone. Okay? But as we go larger, we go to the university or population, with the new network or with the web graph go larger, how does that change, right? So surprisingly, this change actually in a log scale means that, right, when the number of nodes in the graph increase, right, exponentially, right, the diameter only grow linearly, right? So of course, the question is that why do we have such short paths, right? So this is very different from the physical network. For example, the physical network, like a road network, if you just travel locally, I mean at Stony Brook, right, the average distance, right, consider that average distance compared to if you travel across New York State, that average distance, or if you travel across the United States, the average distance. Clearly, that almost grow linearly, right? So, uh, but here on the web graph or the social network, actually the diameter, the average distance only grow in this kind of a log scale. Right? If that's the case for physical networks, that's perfect, right? That means if you on average take 1 hour to travel within the Stony Brook, maybe not 1 hour, maybe 20 minutes, right? Then if you go to New York State, it's not like 10 times larger. It's just slightly larger from 20 minutes to 30 minutes, right? It's kind of grow linearly, right? That would be really nice, right? But unfortunately, in the physical network, it's hard. Right? Then the question is that why in the social network, in the virtual world, right, we can have this benefit of luxury to have such short paths. Okay. This is a question we will explain later when we introduce you to the uh, network model degree. So the degree is the related to connectivity, right? So it tells us the importance of nodes and also the density of the graph. Right? If the degree is high, right, on average, then the graph is dense, right? Versus if the average degree is low, then the graph is more sparse. Right? But it's also the degree is not evenly distributed, right? Uh, some nodes are more important, and normally they have more degrees, higher degrees. Right? The degree is just a number of edges connected to that node. Right? There are two uh, notions of degrees for directed graph. One is in degree, the other is out degree. Right? So consider it's you follow someone or someone follow you, right? So it's different. For the web graph, right? You can easily create a graph, right, to point to many other graphs. The out degree is very high, but it's not that easy to get the in degree, right? Especially have the in degree from important web pages, right? So this is the part that's very important to Google PageRank. So here we want to also look at the degree distribution, right? Of course, you can guess, right? What is the degree distribution? Right? One guess is that it's a normal or Gaussian distribution, right? Because due to the central limit theorem, right, you get the normal distribution. Right? So everyone is more or less the same. Is that right or wrong? The question is that the intuitive guess of the degree distribution in web page or in the social network should be normal distribution, right? Because of the central limit theorem. If you have a lot of random uh, variable, right? You sum them together, it's go to a normal distribution. Question for you guys, is that right or wrong? Right? So we saw one answer, right? No, it's probably right. It's probably not a normal distribution. Why? So because you can observe there are some web pages are very popular, right? They have a huge amount of integrated distribution. Right? Because this is a very good observation. Because for normal distribution, what does it mean? Normal distribution have a typical value. And if you deviate from this typical value, then the probability decay very quickly. Right? So that you know if you go out of 3 sigma, it's very hard, right? But in this case, we probably say that you can go with 100 sigma, right? So our average, maybe the node degree as we discussed is 7. The sigma less is 10. But you may find a node that with 1,000 or even more than those in degree. Right? Or you can just create a web page that has the out degree that is over 1,000, right? So how to do that? You just on that page have over 1,000 links. This is a web page. On social network, similarly, right? You see some very famous people, they may get followers like millions, but on average, people may just get less than 10 followers, right? So which means, right? So compared to the average value, right? The dream case is really, really high, right? So in this case, it gives you the indication it is a heavy tail distribution, not a normal distribution. Right? We will discuss this later, right? But just as a advertisement, right? So the word is not even though they call it like a normal distribution, seems like a normal, but no, right? Most of the distributions in the world, naturally, they are heavy tail. They are not normal. We will talk about that why later in the class. But knowing this is very important because for the limited distributions we saw, right, it's a normal distribution, like the height or the weight of a human beings. Right? Uh, to make it even worse, right? In the school also teach you guys, right, more on the normal distribution. Even research papers, people focus on normal distribution. Right? But the real case is that many distributions are not normal. But our mindset is already pre-trained, right, to consider medicines as like a normal or Gaussian distribution. Right? This will give a very uh, negative impact when you actually go into the real world. So it's a very different mindset. Whether you consider a lot of things are normal distribution versus they are heavy tail distribution, because under different these two different scenario of the mindset, right? What you should do is very different, right? So, right. So like for example, right? Why the VC world is so successful now, right? You know that for successful VCs, their average return is way more than the others, right? And also, right, their failure rate is also very high, right? How could it possible, right, to have both at the same time? High failure rate, but also very high return, right? This one, if it's a normal distribution, you cannot do it, right? It's because the return on a startup company is a heavy tail, right? So we will talk about that later, but it changed a lot of mindset. And because on one way, if you consider everything is normal, then you probably want to play the safe card, right? But if everything is medicine, not everything, if most of things are heavy tail, right, then you probably want to take more risks. So, right, very different mindset. And for the no degree, this is one real case that is actually normal heavy tail distribution. In particular, it's actually power law. Right? The power law is that the it is linear on the log scale. Uh, there is one variable you need to highlight. So this one should be log. Right. So what does that mean? Right. So uh, the log scale. Let's see. This is a power law. Okay. Let's first look at this one. I think this one is for the exponential distribution. Right. Okay. So what does that mean? Exponential is like this. And if you take a log, right? So it's a semi-log, right? When you go to this one, it's like this, right? But if you also do the log scale on this one, it decay very quickly, right? So because it's a linear, you see already like this, right? If you uh, do the log, basically you take the log on both sides, right? So you can see, right, it's very, very small. But this is exponential. What we say that for the raw data on the degree is that it's a linear, but it's on this log scale, not the log linear scale. the tail, right, is a little bit different, but generally speaking, you can say it's a log scale. So what does that mean, right? So we can get the equation, right? If it's a linear or log scale, you can write in this way, right? The log fx you can consider as y, the log x consider as x, right? Y equal to minus alpha x plus b, right? Minus because it's a the slope is negative. And then you take exponential on both sides, then basically you get this one, right? So you say this is a constant times x to the power of minus alpha, right? This is a power law. And when you vary alpha, right, then you can also get a different shape, right? So basically, all this is also called the Pareto distribution, right? So you can see in this way, and the normal is in this way, right? The difference is that the Pareto distribution, the tail can go very, very, very long, while the normal distribution, right, it quickly decay to zero. Now let's talk about some differences between heavy-tailed distribution and light-tailed distributions. So heavy-tail means that you have a large variance, right? So uh, compare the probability, right? Compare with normal, or even you can have the exponential, right? That it's larger than x. X can be a very large number versus a Pareto distribution larger than x. And this probability is much, much larger, right? Go to infinity. It also tells us there's huge difference between the max and the mean samples. Right? For example, if you sample human height, right? This is like a normal distribution. So the max, the highest people versus the shortest is roughly five, only five times. But if you consider city, right? So some cities are huge, right? Like a Paris, right? It's probably half of the whole country, right? Versus they are very small cities, right? The city may have a very small number of people, right? The max and mean is over 100,000, right? Or if you consider that one, that is wealth, right? The I think some news that says Elon Musk is on the track to become the first one to have $1 trillion as a net worth, right? In maybe 10 years, right? But even now, he has probably $200 billion. Minimum is negative or zero, right? Even if we consider the average, right? The average probably is 200K thousand, right? That's already not that bad, right? As a net worth. But you can see, right, from a billion to K, right? It's a this case is a 1 million difference, right? For this one, I didn't consider me because the me can go to zero or even negative, right? So you can say, right, this is one thing that is very different. Or if you consider the company, either size or market cap or their revenue or the number of employees, right, it can vary a lot, right? Several magnitude. Versus for human height, human weight, right, those normal distributions, right, five, right? Actually, think about anyone else can give me more example of a normal distribution. Right? You can put it in the chat. Because I know later I will show you a lot of heavy tape distribution. Right? But here, I like you to think about more like normal distribution. What else are normal distribution? Right. While you're thinking, yeah, let me also try to get from ChatGPT. right? You can do that as well, right? So actually, right, I can show you guys. Right, the normal distribution of the bell curve, right? So it's a many natural phenomena measurement errors tend to follow normal distribution due to the central limit theorem, right? And also you can say height, right? We discussed IQ score, blood pressure management, right? Random errors, test score, weight of the manufactured product, right? Daily temperature, errors, right? Financial returns, human body weights, the measurement, crop year, right? Reaction time, right? Right. So it also explains why this is common, right? So this is, as I mentioned, this is due to central limit theorem, right? It's that the sum or average of a large number of independent, identical, distributed random variable, right, tend to be normally distributed, right, regardless of the original, right? But from here, you can say, right? So actually, there are not that many, and the error, many of them related to error, and or take some average, right? Uh, but did you see anything that common here? I know this may be a little bit more challenging, but basically, right, those distributions, there is actually an underlying kind of a feedback, something like that, right, to control it. Right? Why the height of a dot, right? Those turn to be normal distribution, right? Because there is a huge disadvantage in survival if you go to extremes, right, for your body, especially if you go to very high. The IQ score, you probably heard about the return to normal, right? Right. So basically, even to parents are have really high score, their kids may return to normal, right? Blood pressure, right? You, at my age, you start to realize that the blood pressure can really go to very high, right? Unless right, you try very hard actually bring it to normal, right? So the reason you say it to normal, it's not that they cannot go very high. It's basically if you go very high, the people may die, right? And also before that, your body have a lot of mechanisms, or even you use some medical treatment, try to keep it within the normal range. Like the test score is something like you keep it in this way, right? Because otherwise, if you keep giving the question that some student can do it, give a very high score, right? And also it's probably related to the IQ as well. The temperature, right? So if you look at the history, the temperature on Earth actually vary a lot, right? In extreme case, it can go to like 1,000 degree or even higher, right? But at that time, there is almost no creatures, no living things on the world, on the Earth, right? It's it's basically only the temperature is within a certain range and its normal distribution that we can survive. And that's why we observe it like a normal distribution, right? The financial returns, right? In normal days, yes, but think about the financial crisis, right? So, right, if you consider that as a normal distribution, you probably will have a very big surprise in your life, probably more than once, right? And that will have a very bad situation, right? The human body measurement, right? Like other, but that's because if you go to extreme case, you cannot survive. Right? So there is something that limit you from going there. Right? So basically, I hope you can get what I'm trying to say. Right? So actually, the normal distribution is not that natural. It's not that normal. Actually, you need to have something there to help you, right? To have feedback or something in order to have the normal distribution. Actually, if you don't have those mechanisms behind those, right, the distribution can go very different. Okay. The second one is that the normal distribution is typically around its mean, right? But for the Pareto distribution, there is no typical value, right? That's why if you know the for some company, right? For some, so they often tell you the average income, right? So I think the some survey also show that, right? But the underlying assumption is that if the income distribution is normal, then you probably can trust the value, right? If let's say the income distribution is a normal distribution, and then the average value is 100,000, then you probably that the information tells you that if you join that company, you will earn something around that value. Right? But if I tell you it's a Pareto distribution, right? I tell you the average value is 100,000, right? It probably won't tell you much, right? Because in that case, what you may have is a situation that many people only earn 10K, but there is one person get 1 million, right? If you take the average, you still get 100K, right? But it doesn't make sense to you because in that case, right, you are more likely to get 10K instead of getting 1 million, right? So that is a motivation. In many cases, you want to look at the median value instead of the mean. Right. These two vary a lot. Right. Let me try to find you some example in daily life. For example, the average wealth. Yeah, let me, instead of showing you directly, let me copy here because I don't want to show you all at once. I put in the chat. Right. So according to the Federal Reserve, right, the data is shows the average net worth in America is basically roughly a little bit more than 1 million. What does that tell you? Right? So basically, as I just mentioned, right, if the network distribution is a normal distribution, then that is a very good value, right? That means a majority of the Americans, right, should have a net worth around 1 million. That is very decent. right? $1 million, right? But since it's a parallel distribution, right? You know that people like Elon Musk have 200 billions, right? So if you take the average of you and Elon Musk, right? So the average is 100 billion, but it doesn't mean much to you, right? So now let's say the next, as I just told you, right? If we do the median data, right? The median is that's in the middle. If you rank everyone's net worth, right, from the highest to lowest, right, what is the people in the middle? Right, okay. As you can see, this is a significantly smaller. Right? In this case, the median net worth is around 200,000, right? Less than 20% of the average one. This is an example, right? Showing that one is a Pareto distribution, right? So these two very result. If it's a normal distribution, right? The average human height and the median human height is probably the same, right? So for example, let's check. Give me a second. It asks me to log in again. Right, let me share with you, right? So you can see the difference. Right. So this is a average at the medium height. We know that it's a normal distribution, right? So in this case, the global average for men and women, you can say the average is very close to the median. Right. Again, the median a little bit smaller, right? But you can say the trend, right? Versus what we say here, if it's a normal Pareto distribution, the average is more than 5 times of the median. Right? Therefore, if you know something, you suspect even something is uh, not a normal distribution, right? So tell you the average doesn't mean much. Okay, let's continue. So there is no typical value. I hope you remember this one because in daily life, you will see again and again, right? People just use the average value, right? It's a mean, not a median, because a median is really more important, right? In most cases, right? So, okay, the last one we want to talk about the property is called clustering. Right? This is a little bit more complicated, right? I hope we will do some calculation in this lecture. I hope you can uh, understand the concept and know how to do that. Right. So the classroom try to capture right the communities right in either the web graph or in the social network. Right. The cluster just means that a set of nodes that they are highly connected to each other. Right. In dream case, it's fully connected. Right. If three nodes, the best case is that they know each other. Right. So it's a triangle. This is a four node fully connected graph. Right? This is a five node fully connected graph. Right? So, uh, of course, this can be important for search engine, right? Uh, because when you search for tiger, right, you want to get a result about animal and about sports, right? So there are many other things. You don't want the result all from the same cluster, right? So now we define the clustering as a notion of a cliqueness, right? And so to get this kind of fully connected components. So high level, right? We say a graph is highly clustered if it is much more likely than a random graph for this clique fully connected small component to exist. Right? Of course, we need to explain in more detail what we mean by a random graph, right? By this. So, but at the beginning, right? So the question is that should we expect the web graph to be highly clustered? Right? Of course, you can say the answer is yes, right? Because if web A links to both web B and C, it is more likely than normal that B and C are related, and thus they are connected as well. Right? Which means if there is a edge between A and B and A and C, so it's more likely to have an edge between B and C. Right? Similarly, on social network, if A and B are friends and A and C are friends, it's more likely than normal, right? That you randomly pick two people, right? And B and C are more likely to be friends than to randomly selected people. Sorry. Okay, now we talk about some real calculations, right? So what we just said is just very vague, not quantitative. Right? Quantitatively, right, there are two common definitions, and we will have question for you to give you a graph to calculate the cluster coefficient, right? So this is, as we mentioned, on quiz 3, you start to have some question that is not multi-choice, right? This is one example. Okay, definition. One is called overall clustering coefficient, right, of an undirected graph G. Is calculated in this way. Right? Three times the number of triangles in the graph. Right? Okay, this is not for advanced mathematics, but others, but instead the elementary mathematics. Right? Can you count the number of triangles in the graph? Right? And then divided by the number of connected triple. What do we mean by connected triple? Right? It's basically three nodes, they are connected. Whenever you see these three nodes connected, so there is a possibility that you form a triangle. Right? Actually, in one triangle, right? If a graph is just a triangle, right? Right. So the number of triangles in this graph is one, and the three times one divided by how many connected triples here, right? So there are actually more than one because if you consider BAC, they are connected triples, A in the middle. Or you consider ACB or CBA, right? They are all connected triples. So there are three connected triples, right? The first one is BAC. The second one and the A, C, B have C in the middle, and the last one have B in the middle, right? A, B, C. right? So basically, there are three connected triples, right? That's why you have these three here, because for each triangle, you have three connected triples. So in this case, the graph is fully connected, then you get it as one, right? So you can count, right? So if we have four nodes, right? Fully connected graph, right? Then how many triangles do we have? Right? We have one, two, three, four, right? So 3 times 4. How many connected triples we have, right? For each node in the middle, if, for example, if you consider node A in the middle, it is connected to three edges. Among the three, you just choose two edges, right? For example, you can have this one as a connected triple. You can have this one. You can have this one. Three of them, right? So basically, three choose two, and the four is the same. So you can say you also get one, right? Further, if you want, you can uh, here. Or you can say, if we go further, right? If you have five nodes, this is also fully connected, right? In this case, how many triangles we have, right? One. Oh, that's a lot. So from this node, we have one, and it's hard to count. One, two, three, four, five. This is another one. Yeah, you can count with me, right? So one, there are also five like this. And I think there are total, right, 10. Right. So there are 10 triangles. This 3 times 10 divided by, for each node, 5 node. For each node, you choose 2 from this one. This is 6, right? So 5, 6. This also equal to 1, right? Basically, for fully connected graph, right, using this definition, its overall cluster coefficient is 1. But if you remove a lot of edges, for example, if you only have this one, right? What is the overall cluster coefficient here for this graph? This is 0, right? Because there is no triangle here. Okay, add one edge. Right? By adding this one, now we have two triangles. Right? So the numerator is 3 by 2, and then there are different situations. For two nodes, they are choose 3 by 2. And for the other two nodes, there are only one of them. So 6 divided by 6 plus 2. Right? So 3 by 4. Right? So basically, this is a calculation you want to do enough, right? So that given any graph, you can be able to calculate the cluster overall cluster coefficient. Okay, this is consider the whole graph, right? All at once. So there is another one that is called the average. Right? Means that we calculate the clustering coefficient for each node and then take the average. Right? So uh, so for each of them, it's basically the number of connected connected triples centered at this node and how many triangles it for created. Okay. So let's consider this node to calculate this one. First, you can calculate the overall class coefficient, right? To see if you get the same answer. Right. Only one triangle. Right. So 3 times 1. And the connected triples at node 3, 1, 2, 3, 4, 4 edges, you can choose 2 of them. Right. 6. Right. And for 4 and 5, only 2 nodes. And then this is a connected triple, and then this is a connected triple. Right. So it's 3 divided by 8. Right. You get this amount. And if we do the average cluster coefficient, we need to do for each node. For 1 to 2, there is no connected triple centered at node 1 or node 2, then we define that as 0. Right. For node 3, 3 it actually have 1, 2, 3, 4. You choose 2 out of 4. There are actually 6 connected triples centered at node 3. Among the 6, we only create one triangle. Right? So this one is 1 divided by 6. Right? And for 4 and 5, there is only one connected triple centered at node 4 or 5. And we actually have one have one triangle form. Right? So both of them is 1. And then you take the average, you sum them up. It's 13 divided by 6. Then you take the average divided by 5, 13 divided by 30. Right. Any question about this? Now let me give you a practice to do it now because it's something I really hope you can understand. Now I add one edge between 2 and 4. Calculate the overall cluster coefficient and also the average cluster coefficient. In 3 minutes, we will work on this together. You have 3 minutes to finish it. Okay, I did it. Right. So yeah, I, yeah. So let's say if this is what you get. So the first one, overall class coefficient. There are two triangles here, right? And so 3 times 2, right? That is a numerator for overall class coefficient. And for the denominator, right? We count each of them. So right. So connected triple at 1, 0. Right? At 2, there is 1. 3 again is 6. But note 4, 3 edges, it increase from 1 to 3. Right? The 5 is still 1. So you sum them together, right? So it's 11, right? 6 divided by 11, right? So this is a increase from the original 3 by 8. Right? So this is a 0.375, right? This one is 0.5, something like this, right? So it's an increase because now we have more triangles there. For the average, right? Let's count one by one. The node 1, the average class coefficient is still 0. Right? 2, 1 connected triple and get one triangle is 1. For 3, among the 6, we get a 2 triangle. Right? So it's a 2 divided by 6, it's 1/3. For 4, among the 3, it creates a 2 triangle, is 2/3. And last one, 5 is 1 connected triple, and 1 is 1. So sum them together is 3 by 5, 0.6. Right. The original one is probably 0.43, something like that. Right. You see, both of them increase by adding more edges. The other message you can get is that actually by if you compare the overall class coefficient and the average, these two are not far from each other, right? So the question here, can you create a graph where the two, where the difference between its overall cluster coefficient and the average is very large. So the next lecture or maybe next Thursday, so I will ask you because next Tuesday is our update. Right. So get this one, think about this one. So we will compete among ourselves, right, to see who can create a graph where the average class coefficient and it's very different from the overall class coefficient. Right? Note that so this range is between 0 and 1, right? So let's say who can get a very different one. Uh, right, there are other ways to do that. Right? So you can add the edge here. Right. So by doing this, so if you get 1 or 2, the overall is now we still have two triangles. Right. If you count the kinetic triples, right? 1 now it's 1, the 6, right? So it's 3 divided by 5. The average class coefficient because 1, 2, 4, and 5 are all 1, right? Then for 3, 6 of them, you get 2 triangles is 1/3. So you take the average is 13 divided by 50. Right. So this is this calculation. Right.
I have a quick question.
Go ahead.
I'm a little bit confused on the triples. Like, could you go to the previous example, like the previous slide? So, yeah, in this one, so there's 8 total triples. So I understand that we get 6 triples from the triangle. Um, but so why do we only have 2 more triples? Like, aren't like we could have something like 1, 3, 2, and then 2, 3, 1. But then we could have also something like 1, 3, 5 and 5, 3, 1. Right? Does that
Uh,
not count as?
you mean this six?
Well, we're right. The 6 is just from the triangle, right? The
No,
six
this
triple
six is from the triples centered at the node 3.
centered at 3.
Right? If you consider 3 in the middle,
Mm-hmm.
the connected triples, right? You can pick the other 2 nodes, right? There are 6, the remaining 4 nodes you can pick, right? Because they are all connected. Out of the 6, you choose 2,
I
right? There
see.
are 6
We're
of
only
them, right?
getting, I see. We're only getting 3 from the triangle. The triangle is providing 3. The other 3 from 3 are from using 1 and 2. Okay, I got it. Makes sense. Thank you.
Yeah, you can do that way, but I think the easier way is just you count for the connected triple centered at each node.
Right. Yeah, that makes sense.
That's
That's
easier.
probably the easiest. You're right.
Good. Okay, so I guess because this one is already fairly complicated, I suppose many students may have some challenges in calculating this one. And so if you have question, go to the TA office hour or my office hour. Right? We are happy to guide you through the process, right? Doing this calculation. Right? It's uh it's not that hard, right? Compared to like the uh, calculus or those formula you did, but it still needs some effort. Right? Otherwise, yeah, it's not trivial. Okay, for next Tuesday, we will have our midterm check. So as we mentioned, because we have a lot of groups, so each group you may have 2 minutes. Basically, by the way, I will give assignment that you need to submit your material either in the slides or that can be in the document, but limit to 2 pages to summarize what are your deliverables. Right? You may update it from after getting my feedback, right, from your original proposal. And what you have done on each of the deliverables, and what is your plan to finish all of them by the end of the semester, and any challenges or changes. Right? So just be so basically next Tuesday when we go in through that, then you can see how each group your fellow students are working on this. But basically, I will give 5 points for that midterm check because I don't want you to delay everything until the end. Right? So that is actually a very bad indicator for your performance. Right? So it's already for next Tuesday. It's already the ninth week. Right? We already halfway past the whole semester, more than halfway. Right? So by that time, I think roughly you should finish basically 1/3 of your whole project. Right? If you're doing better than that, great. But if you haven't done much on this one, you may get a low score on your progress, right, for your project. Right? So you still have several days to catch up in that case. And yeah, so I look forward to your presentation next Tuesday. And after that, as I mentioned, we will start to have some guest speakers from faculty members in the data science program. Right? From there, you can also have a chance to learn more about the data science, those system applications, right? And also get to know our faculty members. So for especially for our data science student, that is hopefully useful, right? For your if you say you want to do some research project with them, or maybe some question you have for them. What do you handout left? Challenge. Recap. Yes. So don't have more than 3 slides. Make it concise so we can directly to the point. Basically, it's a check and hopefully I have some time to give you some feedback, right? If your slides is concise enough. So also, yeah, you can send me your slides beforehand, or at that time I can have the slides in my email. Then we can save the time for the switching. Right? So we can use my computer to do that. Okay. Any last minute question? I believe we should be able to get through all the predictions, right? Because each one 2 minutes, we have not less than 30 groups, right? So it's also an update. We should be able to do that. Right? This is something also I want to do that in person, right? Because you can see from each other, right? How it improve and how people handle the different challenges. Okay, if no more question, I will see you guys next Tuesday and look forward to your update. See you then. Bye.